Okay, let's start the seminar. Let's start it by some exercises about projective dimension. I recall that projective dimension of module is just the maximal, supremum of length of projective resolutions of M over R. Yes. And it's not greater than n if and only if all x from m to some n are 0 for e greater than n. Okay. Now the first exercise we proved last time. It's the most general comparison theorem for projective dimensions. If we have ring homomorphism between two commutative rings, yes, maybe here I suppose that all my rings are commutative for simplicity. And M is S module. Then I have projective dimension of M over R. I have projective dimension of M over S, and I have projective dimension of S over R because S is and M are R modules through this homomorphism. And I have this inequality. We proved it. It follows from change of base spectral sequence of something of this form. Yes. S yes, something like this. R Q. Just 1 second. Home from. No, maybe something like this. M X Q over R to S to N. For any R module N and S module M, we have spectral sequence with this second page convergent to X P plus Q over R between M and N. And so if we know that this X vanish in these dimensions and this X vanish in this dimension by this definition, then we obtain that this X vanish in this dimension and we obtain this inequality. Okay. This is the first. We proved this last time. No, we reproved this again. Now, this is because of O. This is because of our general spectral sequence, of course. Now, let's prove more directly another properties. Second exercise is something like if X is non-zero divisor in R and M is R modulo X module, it's the same thing as R module with this property that X by 0. Then, and of course, if projective dimension of this module M over quotient is finite, then we have the following equality now. Then projective dimension over R exactly 1 greater than projective dimension over quotient. This is important because, for example, if we consider R is Z, X is 4, and M is Z modulo 2, then projective dimension over z of z modulo 2 is 1, but projective dimension z modulo 2, of course, is a module over z modulo 4, and you can calculate that all x and all tor between z2 and z2 over z4 are non-zero, so projective dimension is infinite. So we have no equality here. But if this projective dimension is finite, then I claim that the equality holds, and and we can prove that by induction on this finite number. Okay, proof. Induction on this projective dimension. Okay. Well, first of all, because we know that xm is 0, then m is not projective. Because for projective, because x is non-zero divisor in R, so x is non-zero divisor in free modules, and so x is non-zero divisor. No, x cannot x by 0 on direct summands of free modules, so it cannot x by 0 on projective modules. So from this we know automatically that this projective dimension R is non-zero. Of course, it's not projective R module. So this makes sense, because by this formula we obtain that this number must be not less than 1. It's true. Okay. It's not projective. Okay, now induction on M, on this number. So base of induction. Base of induction if this is 0, if this is projective over R modulo x. M is projective over R modulo x. Then if it's projective over R modulo x, then in fact its projective dimension is equal to projective dimension of free modules, and projective dimension of free modules is equal to projective dimension of R modulo x itself over R, and this is 1 because it's non-zero divisor. We have resolution of length 1. And from this you can easily check this. If you don't believe this, it's exercise. Okay. So we obtain that this is 1, this is 0, and the equality holds. So base holds. Base is true. Now step of induction. Okay. Step of induction. And step based on the following general observation. If we have short exact sequence of modules, then how we can estimate projective dimension of of one of them through projective dimensions of two others? And then we have the following inequalities. Projective dimension of B is not greater than maximum of projective dimension of A and C. Projective dimension of A not greater than maximum of projective dimension of B and projective dimension of C minus 1. And projective dimension of C not greater than maximum of projective dimension of B and projective dimension of A plus 1. It's easy to see from this definition, from this property, and from long exact sequence of X for this short exact sequence. So it's easy to see. Okay, now we can use these estimates. Okay, it's what we need. Maybe So we want to do the step of induction. So consider if we have some module M, then we can consider the following short axis sequence over R modulo X. This is our model. This is projective. Projective R modulo X module, and this is the kernel. So first of all, and yes, and of course, it's also the no, if you want, from these equalities, also follows that if this is projective module, if it has projective dimension 0, then of course projective dimension of this module exactly one less than projective dimension of this module. No, this is always true. It's also easy to see from the sequence next. Okay. Now, so this projective dimension one less than this projective dimension, and we have induction on this number. So by induction assumption, we can assume that this projective dimension is equal to projective dimension over R minus 1. Okay. So what we need to check that we need to check that this thing is equal to projective dimension over R M minus 2. So in fact, we need to check that projective dimension of K over R is equal to projective dimension of M over R minus 1. So what we really need to check that projective dimension over R is also exactly 1 less than projective dimension of M. It's our question. Okay. No, but we know that again, because this projective dimension, this is projective module over R modulo X, so it has 0 dimension over R modulo X. But again, it has the same, what the projective dimension of P over R. No, again, it's the same as the projective dimension of R modulo X over R, and this is again 1, because X is non-zero divisor in R. So we have no, maybe we have no such equality, but we have estimates. And from these estimates, in fact, what we have? No, maybe exactly. Let's see. We have now consider this short axis sequence as over R over R, and we have P K. Oh my God, K M. This is P K M P K M. This is unit. So we already see that projective dimension of M and K, no, of course they are not projective. So projective dimension are not 0. Here we have that. No, yes, this is unit. It's 1. It's also 1. So, for example, from the second equality, we obtain that projective dimension of K is not greater than projective dimension of R minus 1. Maybe it's unit. Okay. Then I just say that, okay, from these inequalities, and from our knowledge that projective dimension of R of K and M greater than 1. No, what I want to say that the only possible, no, if either we have this equality, or we have only one possible exception. And one possible exception, it's only if inequality, if this equality star, either star holds, or in fact the counterpart situation is only possible if we have that projective dimension of M and projective dimension of K are both equal to 1. In this situation, then we have this is maybe 0, then it's maybe 1, this is 1, this is 0, and it's possible. In all other situations, in fact, from these equalities we obtain that this equality holds. So we need to check that this is impossible. In our situation, because if it's possible, that it's counterexample for our equality, but it is the only counterexample from these inequalities. Okay, in fact, we can check even that this equality is possible, because in fact projective dimension of M cannot be 1 because this model is not projective. It's model over R modulo X, so it also cannot be projective over R. So in fact it has more than one projective dimension. No, okay. Now let's check this. If it has projective dimension 1, why it's not possible? No, this means that we have projective resolution of length 1 of R. Over R. Now then, if I apply tensor product with R modulo X and obtain short X sequence of this tensor product with Tor long X sequence, then I obtain Tor from over R from 1 to R modulo X. No, it's 0 because this is projective module. Goes to Tor 1 R M R modulo X, and then P1 modulo X, P0 modulo X, M modulo X. No, but this module, no, Tor 1 with R modulo X, where X is non-zero divisor of R, is just extortion of M, but we know that X acts by 0 on M, so it's M itself. It's M itself. Okay, and why it's not okay? Because we have such exact sequence of R modulo X modules. This is projective R modulo X modules. No, okay, we have something like projective dimension of from the previous one we have that 1 second. Maybe we have something like RS, RM, dimension of R modulo X, M plus projective dimension of R modulo X by R, and this is 1. So in fact, we have that projective dimension of R, it's from the previous general equality. So we have that this projective dimension is 1 greater than this projective dimension. And so if, no, yes, and if, no, yes, it's very strange because no, if this is unit, then this must be 0. So it must be projective R modulo X module. No, in fact, if it's projective modulo X module, then no, okay, no, no, it's impossible. For example, no, maybe. О, привет. Мы делаем первое упражнение про проективную размерность. No, yes, it's really impossible because, no, yes, from the previous one we obtained that if projective dimension of M is 1, then this is 0, and no, then it's projective module, and because of this, we obtained that, in fact, if you have some resolution, you have some exact sequence of length more than 1, then all these models must be also projective. But no, this model is not projective. Is not. No, sorry. Stop. Это не нужно. Yes, of course. Sorry. Yes. Yes. From the previous one, we obtained that this model must be then projective, but we know that no, this is not projective because it's not induction of step, but no, we know that if it's projective, it's our base of induction, and we know that if it's projective, then the equality holds. And now we can assume that equality does not hold, so it's not projective. It's projective, it's all okay. And this equality cannot hold because this equality is a counterexample for this equality, but this equality holds for projective model, as we've seen for in our base of induction. Тебе повторить или это можно пропустить упражнение? Но потом можешь посмотреть. Значит, okay, so so this is cannot exist, and then from this equalities we obtain that this equality holds. Okay, this was the following exercise. It was the following exercise. It was that projective dimension of R M is projective dimension no, sorry. Stop, 1 second. 1 second. No, sorry, it's what was not correct. Sorry. We need this equality. This equality. plus 1 if it's finite and this is not the redivisor of in R. Yes, sorry, the last step. Yes, we have that from this inequalities we obtain these equalities. Okay. No, yes. And from this and from equality of by induction equality on K, we know that for K, projective dimension of K is equal to projective dimension of R modulo X. So from this equality, we obtain that this projective dimension is 1. And from this equality, that this projective dimension is 1, we obtain the contradiction because, again, yes, sorry, we have projective resolution of length 1 when we have short, long exact sequence. And because this projective dimension is equal to 1, then if we have this long sequence, this must be projective because it's longer than 1. But this is M, and we know that this model is not projective. Sorry. This is correct assumption. No, I say that we prove this by induction. By induction on this number. No, if it's projective, then it's okay. Then by induction, we consider kernel. No, have some projective surjection. I consider kernel. By induction, we have this equality. We have this equality by induction. And we have these inequalities, general. For any short sequence, we have these inequalities. And from these inequalities, we have seen that the only counterexample for our equality is this situation when it's both 1. No, you can check that this is only possible counterexample. And then from this and from this, we obtain that projective dimension of M over R modulo X is 1 and modulo R is 1. But this is impossible because if it has projective dimension over R 1, then we have such projective resolution over R. And after R modulo X, we obtain this long sequence with Tor. This Tor is M itself because it's extortion, and I know that M is module over R or modulo X, so Xm is 0, so it's all torsion, extortion. And I have this X sequence over R modulo X. This is projective, and this dimension is 1, so it must be projective by one of the exercises. If you have then this is not projective because we assume that it's not 0 dimension, so it's contradiction. It can't happen. Okay. This equality. Yes. It's a little bit stupid possibility, but it can't happen, of course. Okay. Now did you do some exercises? What? Okay. Тогда the third inequality of projective dimensions. Now, if X is non-zero divisor in R and X is non-zero divisor in M. In the previous situation, X acted by 0 in M. Now it's non-zero divisor in M. And then projective dimension over R is not less than projective dimension of M modulo X over R modulo X. Now we prove this by induction on this number. So if it's infinity, this is holds. So we may assume that this number is finite, and so we can use induction on this number. No, yes, and this is the previous equality does not hold for infinite projective dimension. It's Z4 over Z and over Z2. Okay. Now, if this module is projective, no, sorry, no, yes, if it's projective over R, no, then this module is projective over R modulo X, in fact. No, if M is direct summand of free R modulo, then Mx is direct summand of the same free modulo over X. No, after modulo by X, we obtain free modulo over R modulo X and the same direct summand. Plus something is free module. No, then after modulo X, you obtain that it's free. So if this is 0, then this is 0. So base of induction is okay if it's 0. So step of induction, step. Now again we consider the following short-order sequence with projective middle. This projective dimension is 1 less than this projective dimension. X is non-zero divisor in this module, so by induction we have that this is this one. We have this inequality. No, in fact, this exercise is easier than the previous one because now it's almost all. So again, I consider exact sequence of Tor after tensor with R modulo X of this short-order sequence. I have Tor 1 between this and R modulo X is 0 because it's projective. So in fact, I obtain again this long-order sequence. This is more or less the same argument. But now, no, this is extortion of M. But now we know that X is non-zero divisor and M means that extortion is 0. So in fact, this is now a 0 module. So we have this short-order sequence. No, and from this short-order sequence over R modulo X, and again, this is projective module, we obtain that this is exactly 1 less than this projective dimension over R modulo X now. No, and so we obtain inequality. Okay? Here it's easier than the previous one. No, a little bit. No, the previous one also, but you need some silly analysis of this, of some counterexamples where it's 1 and 1 and 1 and it's impossible. No, here you don't have to do this. Okay? Так. Now from these things we can obtain the following easy consequences. For example, if we consider a polynomial ring, well, then projective dimension of a polynomial ring of so-called polynomial module, I think that this is more or less clear notation, yes? No, if you have module over R, then I have module in X over R modulo X, yes, okay? No, it's free module. No, if you wish, it's polynomials with M coefficients, and you can multiply polynomial with M coefficients with polynomial in R coefficients, okay? It's module over polynomials, okay? But then that is equal to this projective dimension. No, this is because X is non-zero divisor in this module and in this module. So by the previous one, we have that this inequality, because polynomial modulo X is exactly module and R itself. So this is from the previous one, but also so R X modulo X is R, and this is non-zero divisor. Is the first one. But the second observation that, in fact, this ring, this ring is a free R module, yes. In particular, it's flat R module. And so if I consider some free resolution, if I consider some free resolution of M, if I consider some free resolution of M over R, then I can tensor it with polynomials. And because this is free model, this is flat, so this is also exact, and of course also projective. No, you can assume that it's free modules. And you obtain projective resolution of polynomials. Because this is flat module. No, and so if you have of some length, then you obtain of length not greater than this length. So in fact, you obtain this inequality. No, we see that this always works if you have non-zero divisor such that it's flat model. No, this is more or less the most natural example of such ring. Yes, one zero divisor, and if you consider quotient, then it's flat over quotient. No, yes, this works if R is flat over R modulo X, where X is non-zero divisor. No, this is a little bit strange because in general this is R modulo. R is it's strange that it's R modulo X module. Maybe sometimes it happens.
You mean the opposite inequality holds in
what?
You mean the opposite inequality?
No, yes, because we have some length for M, then we have projective resolution of the same length for polynomial. So the minimal length for R is minimal length for polynomial is not greater than the minimal length for R. And this is minimal length. So this minimal length is not greater because for any length here we obtain the same length here. So minimal may be only less, not greater. Okay.
And so you have this inequality in more general setting.
More general is it's strange situation. It's strange situation because you have some non-zero divisor, you can consider quotient, but you need that R itself is module over quotient. This is in fact strange because you have this epimorphism. So in fact this is module over R, but in this situation you need that R is module over Rx, and this is a strange situation. This is maybe the most natural situation where it exists, but okay. So you need some section of this quotient. It's more or less polynomials. Okay. And the last one is now in our graded or local situation when we have Nakayama lemma. In this setting, we have the following thing. Now let A is evenly graded, yes, connected, non-positively graded, commutative, because all our rings is commutative for simplicity. Okay, algebra. M is non-negatively graded A module. And so now X is some homogeneous element of positive degree, non-zero divisor in A and M. We proved some minutes before that in general in this situation, if it's non-zero in A and M, so projective dimension of M over A is not less than projective dimension over quotients. But in fact in this situation is equality. So we need to check the opposite inequality. So to prove this, we need to check the opposite inequality. No, so again, if it's infinity, it's true. So we can assume that it's finite, and we will use induction on this number. No, again. No, now. No, yes, again we can play the same thing. We can consider short extra sequence. Oh, I didn't. Yes, but the same thing. Again, it's not zero divisor. It's zero, and of course, in fact, we obtain such extra sequence over a modulo x. And so, what does it mean? This means that no, here again projective dimension over R modulo x of k modulo x is one less than this projective dimension. No, and we have by induction we have equality here. By induction, because it's projective less than one, so by induction we have equality here, and from this original short extra sequence we obtain that it's one less than this one. So we have obtained equality. A question: where we used here that it's some special situation because it works always. So maybe we obtain that this is always true, this equality. No, short extra sequence, it's not zero divisor, it's zero, short extra sequence. So this projective dimension over A modulo x, one less than this, and from this over A projective dimension one less than this, and so we obtain equality by induction. Moreover, I can say that in fact this argument is correct. This argument is correct, but in fact, it does not prove for us the statement. Because what's this argument? This argument is a step. We need base, and base is not obvious part of this equality. It's not obvious for projective modules, because for projective modules it says that if this modulus, well, this equality says that if A modulo x is projective of quotient, then it was projective over A. And this is not true in general. But it's true in our situation. And we need to check this now. It follows from Nakayama lemma. So step works always. Step is more or less trivial. This is maybe not so usual situation when base is less trivial than the step of induction. So base is that if M modulo x is projective over E modulo x, then M was projective over A. Again, the opposite implication is always true, but here is non-trivial implication. This is not always true, but it's true in our assumptions. No, again, as I said before, if we have graded models over graded things, then projectivity, flatness, and freeness is the same thing. It's because it's the same. It's all equivalent to say that M with K is 0 from minimal resolutions. So in fact, I can say free here. So if it's free, then it's free. It's what I need to check, in fact. Oh, again, yes, if X is homogeneous, then it's ideal generated by X is homogeneous, and so A modulo X is graded algebra, and so on, and M modulo X is graded model, so on. So it works. Okay. Now, yes, we need some. Okay, consider M modulo X. If it has basis E alpha over A modulo X, some graded basis. Now then I can consider pre-images, yes. I have surjection, so it has pre-images some elements A alpha bar. No, and my claim that this is basis over A. Why it's basis over A? y generates y generates m over a. No, this is the first one. Or maybe, no, maybe, okay, maybe let's start with linear independence. Linear independence. No, if you have some, как это? О, как будет линия независимости? Linear dependency between these elements in M. This is from A. This is graded number. This is graded element, so you can assume this is graded elements. This is graded linear dependency. Now, what does it mean? That means that you can consider quotient modulo x, and you obtain that class L alpha in A modulo x, E alpha is 0. Because it was basis, it was linear independence. You obtain that L alpha is 0 in A modulo x. This means that L alpha all divided by x. So L alpha x of L alpha prime. And now I have that L alpha E alpha bar. In fact, it's x L alpha prime E alpha bar. But now x is non-zero divisor in M, and this is 0. So in fact, I obtain that this is also 0, and this is not 0, and it's not zero divisor. Okay. And so I obtain this new linear dependence. No, and I can do this again, and so on and so on, and I obtain that my coefficients are infinitely divided by some homogeneous element. It's impossible in a positively graded module. So by induction, L alpha lies in intersection of all x k a. No, this is 0. So okay, it's a linear dependence, and why it generate? Why they generate M over A? You can prove this by induction on dimension. For example, induction on dimension. Or by Nakayama lemma. Let me check this by Nakayama lemma. No, for example, by definition that modulo x is basis, or in particular modulo x is generators. This means that if I consider a module generated at A alpha bar, then it's coincide with M modulo x. It's plus x M is equal to M. Do you agree? Because modulo x, it's generate my module. No, it's equivalent to say that E alpha generate M modulo x over A modulo x, in fact. No, from this it follows that in fact, if I consider not modulo x, but modulo all A plus M, it's also M, no, because it's not less than M, but no, it's not greater than M, because we have. No, here we can use Nakayama lemma, because from this, this equality also it already means that if I consider quotient, then quotient modulo my submodule coincide with itself. No, and from this, from Nakayama lemma, we obtain this quotient is 0. Nakayama lemma says that if you have some module that is same, this means that M is n is 0. And so we obtain this quotient is 0. No, so they generate. No, I think that you can do more or less the same thing by induction on dimension. Again, by induction you have the minimal dimension, then by induction modulo x they generate by something. No, you can use Nakayama lemma, for example. Okay?
In our case, Nakayama lemma is pretty obvious, right? In our case, Nakayama lemma is pretty obvious.
Yes. It is graded Nakayama lemma. Yes, it's yes. Nakayama lemma. It's more or less obvious because because it's increased gradings. A plus increased gradings, and so if your grading bounded below, so you obtain a contradiction. Okay. And now I want to prove lemma for the lecture, algebraic lemma. Okay, this is what about projective dimensions. Okay. Now I want to prove the following lemma. No, in fact, I want to prove the following. No, seemingly a little bit non-obvious fact. Seemingly, I think it seems like a little bit surprising fact. I need the following fact. What theorem? If you want theorem, yes. That. Сейчас теперь мне нужно. Так, что мы хотим доказывать? Again, we have A is even, non-negatively graded, connected, commutative. Do not change that. Connected and commutative. Connected commutative K algebra. Then consider A plus. No, it's all positively graded elements. Yes, it's ideal. It consists of non-zero. Consists of zero divisors. Consists of zero divisors. So any element of positive degree is zero divisor in such situation. Our algebra has this property. This means that for any x from this is also true, but I want to, and I have module. It's not positively graded. A module, and even more, a little bit more, I suppose that A is a finitely generated algebra and M is finitely generated module. A is finitely generated algebra and M is finitely generated module. Then, anyway, surprising statement holds. If A plus consists of zero divisors, no, in M, I mean that this makes sense for any M. So for any x of positive degree, there exists some M in M such such that xm is zero. Yes, it's the same thing. It's definition. Okay. Then, in fact, exists one common M, which then exists one common M, such that such that A plus M is zero, which annihilates all my elements in my ideal. No, of course, from the right to the left it's obvious, but from the left to the right it's not obvious. Yes, it seems like it's strange. No, it's true. No, it's important that it's finitely generated. And now I want to prove this theorem. It will be lemma for our theorems on the lectures. It's a purely algebraic theorem, and it proved by 1, 2, 3, 4, 6 steps. No, not very hard steps. Okay, first step. Okay, let's start. It's the following step. Let me have these assumptions on modules and the ring are common. I will assume that in the whole of my proof. Okay. So the first one, if, for example, let J is graded. No, graded also assumed always, but no, maybe I can emphasize this. Graded ideal in A. And I know that all homogeneous elements, no, all homogeneous parts of my ideal lies in union of infinite union, it's important here, of prime ideals. Prime ideals. Again, if I say ideal, I always mean graded ideal, and if I say prime, I mean graded prime. So this means that if A and B are homogeneous elements such that AB is 0, then one of them is 0. Okay. No, it's a notion in graded sense. Okay. Then, in fact, J lies in one of these ideals. Now here already not obvious part, but here it's important that it's finite number, and all other steps will be about finiteness of such. No, because why is the same thing? Because okay, let me reformulate theorem. Maybe I need to do this now. For any element M, I can consider an annihilator of M in A. Annihilator of M in A. It's all elements. No, maybe in A plus. Okay, such that AM. No, because A0 is K and okay. Such that no, maybe homogeneous. Yes, if it's no, or homogeneous parts. I want its graded ideal. Yes, maybe in each grading I consider homogeneous elements such that it's 0. Yes, it's graded ideal. And this property means that again, maybe any homogeneous element, and here I consider no homogeneous parts of my guess that A plus homogeneous lies in union of all annihilators of all my elements. Yes, it lies. No, any element lies in some annihilator, and what I mean that in fact it lies in annihilator of one element. So in fact it's the same thing, but here of course infinite maybe union. Here it's finite. It's important, and all other steps will be the reduction to finite. No, in fact to see that this inclusion implies that it's inclusion to the finite union. Okay. But the first step it's natural. Okay, so in fact we want to check that in fact A plus lies in annihilator of some one element. So this is natural first step. No, and this step more or less formal. So induction on N. So here it's important that N is finite. So induction on N. No, if N is 1, it's obvious. Yes, there are nothing to prove if N. So we have base, and now we need to step. For example, so step, we can assume that J hom doesn't lie in union of any ij without 1, because if it lies in union without 1, then by induction it's all okay. Okay, for any I, we can assume that doesn't lie in union. Okay, and so what does it mean? That means that I have xj in J, homogeneous element from J without union. Наверное, it's I. Now then, consider the following thing. Consider x1, x2, xn. For example, it's some graded element. It's some graded elements. They have some gradings, and I can consider such power such that their gradings is the same number, and so I can consider sum. Okay? It's a graded element. This is element from J home, because any element is from J. This is from J and this is from J. So this is one element from J home. So it lies in some ij. It lies in some ij1. I don't know. No, J0 is this. No, and now two situations. If J1 is 1, this means that this is This means if J1 is 1, then all these elements is from I1, and so this element is from I1, but this is contradiction because this means that this thing is from I1. This means that XA is from I1, but because I1 is prime, this means that X1 is from I. Sorry. It was in quotient. Then or yes. Sorry, this is the definition of prime ideal. Okay, 0. It was in quotient. Yes. So it's some power in I. So no, this is contradiction. Yes, because I chose X1 sorry. Yes. Yes. Xi lies in EI. Наоборот. Okay, then okay. Let's assume that it's not 1. Okay, sorry. No, this is because J home lies in union of all elements. If I consider not union of all elements except 1, I obtain that this element in this one exactly. Okay, in J and in this one. Okay, if you wish. Okay, I assume that all these intersections are not 0. All these elements exist. So if I consider some elements, it lies in some. If it's not 1, for example, if it's not 1, then all these elements, they all lies in, как это? If it's 1, then this thing lies in 1. Because then XA lies in E1, and so because of sum lies in E1, this product lies in I1. Okay. Then by primary of I, this product lies in I1, and again by primary one of them lies in I1, and this is contradiction. Because yes, and no, because I assume that Xi do not lies in union of all element. Not I. It's exactly in one ideal. Not all. It's a contradiction. And okay, it's cannot be. If J1 is not 1, then it's some of this element, some of this number. Then this, because it's ideal. For example, then this lies in Ij1. Yes, because J1 is one of numbers 2 to n. So xj1 somewhere here, and because it's ideal, this lies in ij1. So this lies in ij1, x1 lies in ij1. This is also contradiction. So it can be happened. So we obtain. So it's contradiction. Contradiction. If it's not in union of all except of 1, it cannot be happened. So by induction to do, it lies in 1. Okay. This was the first step. This is exactly a game with symbols. Yes, it's some formal proof. But it's interesting corollary of this game. Okay. So in fact, it cannot happen then ideal как-то размазан in the union of prime ideals. Yes, it's concentrated only in one prime ideal. Okay. Maybe. And of course, if all homogeneous part lies in one ideal, then all ideal lies in one ideal. Okay. Now the second step. Second step. Blah 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 blah. No, yes, and here in this situation, of course, I did not use that finitely generated. It's not important here. It's important that the number of our annihilators is finite. It's important that the finite generated here. It's finite by assumption. Okay, second step. Second step is the following. No, yes, I need definition. Consider what set of associated primes of my module is set of prime ideals, prime graded ideals, such that P is an annihilator of some element. So it's the set of prime annihilators of my elements of module. No, also graded, of course. M is also graded elements. No, it's the sum set of prime ideals which are annihilator of some elements. Okay. No, so the second one. So I need to check more or less that no, this set is finite, and my zero divisor lies in the union of these annihilators. So okay. So what we need? I have that my A plus lies in union of all annihilators. Here, it's only prime ideals, because here is what is important that they are prime. So my second step is why I can consider only prime ideals here. And the second step is exactly about this. If I is maximal along annihilators of elements, then it's prime. Along annihilators of elements, then it's prime. So in fact, maybe I have some annihilator which is not prime, but then I have no greater annihilator that is prime. So I can consider only maximal here. So I can consider only elements from associated primes here, in fact. This is because of the following observation. No, okay. No, by definition of primary, I have A, B in I. I is maximal along annihilator, so it's annihilator of something. So I have A, B, M is 0. So no, let me assume that A is not in I, so I need to check that B in I. So it's primary. So I need to check that why B in I. It's my question. So let I is not I. So I M is not 0. It's not in annihilator of M. But ABM is 0. So this means that I can consider annihilator of this element AM. And of course, if I have some element which annihilates M itself, then it also annihilates AM. So in fact, I have this inclusion. Because of maximality, this is equality here. Okay? Because it's also annihilator, something that is greater than this one. And also, this annihilator, no, it consists B. B is an element of this annihilator. So B in I. Okay? It's easy observation. So, no, yes. And so any non-zero element lies in some annihilator, and so no, and here where it's the first place where, okay, sorry, I didn't say that, but if A is finitely generated algebra, no, what does it mean? And it's commutative. This means that it's the quotient of polynomial algebra, yes? Of some gradients. No, it's more or less the same thing, yes. And this means that it's a Noetherian ring, because it's a quotient of Noetherian ring. It's important here that, in fact, it's important here is Noetherian property of our ring, Noetherian. So if I have some annihilator, if it's not maximal, I can consider greater, and I cannot have the infinite increasing numbers of ideals. So I have maximal. So any annihilator lies in max. If it's not Noetherian, maybe I have infinite chain of annihilators, and I have no maximal, maybe, I don't know. But in Noetherian ring, any annihilator lies in some maximal annihilator. So in Noetherian ring, because of Noetherianity, I don't know. Then, in fact, this is union of all primes from associated primes. So in particular, in our case, this set is not empty. Because we know that we have zero divisors. Because we know that all our elements are zero divisors. Okay, and now what we need to check, that this set is finite. Is the only what we remain to check. Because if it's a set finite, that by the previous one, this ideal lies in one annihilator, and that's what we need. So we need to check that this set is finite for finitely generated module of a Noetherian ring. No, this is remaining steps. So third step. Third step is something like filtration. If I have finitely generated module, then I have finite filtration. Finite filtration such that quotients are graded, so it's maybe some shifts. No, it's technical. It's not important. Of quotients of my algebra by some prime ideal, and even from associated number. No, okay, let's check this. No, it's because no, okay, consider some no, yes, okay, we know that all our A plus consists of zero divisor. So consider any element of M. It has some annihilator, not zero. It lies in some maximal annihilator. So yes, and maybe I can assume that you consider some element M with maximal annihilator. Yes, so with M and later M with maximal annihilator. It exists by the previous steps. No, and then no, okay, I have. I can consider A. No, it's homogeneous element. It lies in some Ni. So I can consider Ni to M, which sends suspension of unit to M. It's graded morphism. And its kernel is exactly annihilator, yes. So quotient is image, it's submodule. I obtain submodule of this form. I consider submodule, it's M1. It's my thing. Module is P1, it's P1. It's N1. It's submodule of M. No, and then I consider quotient. M, quotient M1. No, again, as all my positively degree elements, zero divisors in M, then there are zero divisors in quotient, and so I can do this step again. Consider some element with maximal annihilator in this quotient, it's prime, and consider again the same thing. And so I obtain some chain of modules with these quotients, and it's finite because it's finitely generated module. if I have finitely generated model of a Noetherian ring, then I cannot have, because my chain is increasing, I cannot have infinite increasing chain of modules. So it might, no, it must be finished by M. Okay, okay. So this is, no, this is again, this is also, this is already the easy observation from Noetherian, because of our ring is Noetherian, our model then finitely generated model of a Noetherian ring is also Noetherian, and I have such situation. From the previous step to second step, I know that in any module I have submodule of the form A quotient associated prime, something like this. Okay, and then by induction I obtain this chain. No, and so maybe the last step, 4 or 5, I don't know. Last step. No, not the last step. It's the fourth step. Fourth step is about, no, okay, I have some filtration. In each step, I have short access sequence. So, and I want to estimate number of associated primes in M itself. So it may be, no, it's useful for me to estimate number of quotients of the middle term in terms of corner terms, and then I need to estimate associated primes of this module, of this elementary module. No, so it's the fourth and fifth step. Fourth step is just following estimate that if I have short access sequence of modules, then associated of N lies in union of associated of M and K. And fifth step, that associated of A modulo P, where P is prime, what is it? It's P itself. It's only P. So from these two lemmas, we obtain that, no, by induction from this short access sequence, we obtain that set of associated primes of M itself is just some subset of the associated primes which exist in this chain complex, or in this filtration. So it's finite. From this we obtain that associated of M is finite, and then from the first lemma we obtain our what we needed. Okay, we obtain that our positively graded ideal lies in one annihilator, one associated M. So we need these two things. Ну, сколько времени там? Не пора еще. No, in fact, okay, in fact, no, this is absolutely obvious. If it's not obvious, you can think about it. It's more or less obvious. It's excess if you want. No, I have no proof of this because I think that it's obvious more or less, by definition. No, so let's check the fourth property. Fourth property, we have the following thing. No, okay. Now let's P from associated prime of the middle term. So it's annihilator of some maximal annihilator of some. Oh no, maybe not. I don't know. I know that maximal prime. I don't know. Maybe prime is not maximal. It's not important. It's annihilator of some n. So no, and let's assume that P is not associated of M. So I need to check that in fact then it's associated for K. Okay. That's what I need to check, that then P is associated for K. No, okay. Consider annihilator of the class of N in K. It's quotient, so in K. No, it's some elements from A plus such that an lies in M. Yes, because then its quotient is 0 in K. Okay. Yes. So but if I have an is M from M, no then так, сейчас давайте скажем P n M prime. Так. No then I can consider annihilator of M. And then, no, of course, if some element is in annihilator of n and M is an, then annihilator of n lies in annihilator of M again, okay? So my annihilator of n lies in annihilator of this, of product of n with something, okay? Okay. So now consider, no, I want to check that P lies in associated of K. No, so okay, let's consider. Let's consider some element from here. What some element x from annihilator of M. No, this means that xm is 0. M is an, so x an is 0. So this means that xa is annihilator of n in my P. Because P is prime, I have two situations. Yes, I have that or x and P, or either x and P or a and P. But no, so if A in P, no, then M is 0. Yes? This means that M is 0. And this means that, in fact, no, this means that, what does it mean? No, in fact, if for any x this is 0, then this means that in fact this annihilator no, this means that I have equality here. Yes? Because I consider any element of no, sorry. So the in opposite direction. If x and p, if for any x in an I obtain that x and p, I obtain equality here. Yes? No, it's obvious. Yes. If for any x I have this situation, then it's equality. No, but then this means that p is prime and annihilator of some element of m. So p is from associated of m. I claim that it's not. No, or maybe I have this situation. Okay, but if it's not this situation, then it cannot be happened. So there exists some x when this is not true. So then we obtain this, and so we obtain then m is 0 automatically. If I have only one such situation, then I obtain that m is 0. But then, no, this means that A lies. What does it mean? That means that no, we want to check that in fact P is annihilator of something from K. No, it's no, I think it's candidate is a quotient of n. What does it mean? That if I have element, no, yes, if I have some element, again, of course, we have where is just P. No, of course, we have this inclusion again. Yes, because if it annihilates n itself, of course, it annihilates quotient. And now if I have some element A from annihilator of n, then I obtain that, in fact, no, I know that n is m, but in fact I obtain that either I have this situation or m is 0. So in fact, I have equality here, yes. So in fact, I obtain that either it's from annihilator of some element from m, from m, or it's annihilator, or it's exactly annihilator of the quotient. So it's here, something like this, yes. No, so yes, we obtain that it's union, and we obtain that this is a strong statement that if all my elements are zero divisors, then in fact all of them is annihilator of one element in my model. And here important, and here it's important that model finitely generated and my algebra is finitely generated, because it's not important. No, I think it's easy. It's not so hard to see counterexamples in not finitely generated situation.